Hey everyone, welcome to SGInnovate. Welcome everyone. My name is David from SGInnovate, and we are very, very happy to have everyone here today. So, 40 years ago, when the first Atari microcomputer was brought to the Bay Area, the small little piece of hardware was brought to someone's garage, and hundreds of people went there and to witness the unboxing and to find out what they could do with the Atari. And that eventually became the Homebrew Computing Club. Two men, Steve Wozniak and Steve Jobs, were regular attendees of that Homebrew Computer Club to share what they're working on and get feedback from everyone else to improve their product. And this is one of the ways in which we want to create our own Homebrew Computer Club. So over the past month, we have dug and flipped every single stone in Singapore to find who are the guys who are working on some AI, who are doing AI work in Singapore. And we have here today people from academia, people representing more than 40, 50 startups in Singapore from different corporations. And we're very happy to have everyone here. And I know a lot of you must be asking yourselves now, what is SGInnovate? This is where I hand time over to our founding CEO, Steve, to share more about who we are.
So I'm very lucky that my name is also Steve. So in addition to Wozniak and Jobs, I'm also a part of this big club. So what I'd like to do is give you 2 minutes on SGInnovate because we're asking for your help. So we are a private limited company with one shareholder called Ministry of Finance. So we are part of Singapore government, but before anybody flips out, we are trying to make sure that we are a commercial, private sector-like company, which is why we are a set-up organization with a private structure. We are not an agency, we're not a stat board. I worked in a stat board for 3 years before this called IDA, and we intentionally set this up to be different. And what we're trying to do is work with those men and women that want to build difficult tech. So we're trying to work with founders that are looking at artificial intelligence or virtual reality, things to do with robotics. So in a nutshell, what we're looking to do is bring academics, entrepreneurs, investors, corporates together. And this space is a way of us bringing people together. So we have 6 floors here. We are also going to be an investor, but for right now, we're trying to make sure that we have people that want to work with each other. So our big belief is proximity matters, and that's why getting this AI-related ecosystem together is one of our first steps. Anything that you think we can do better, we'd like to do it. We don't pretend that this is anything other than version 1, but we're thankful for the big turnout tonight based on friendships and partnerships with many of you. So first of all, thanks for that. What we wanted to do is be content-rich and an opportunity for people to meet each other. So that's why a little bit of food. If you have anything that you think we can improve, which I'm sure you will, it's either Steve at SGInnovate or any of us that are part of the SGInnovate team. Pretty simple. And what we're going to do is try and position Singapore as a place that can build globally relevant products and globally relevant companies. So our basic philosophy is Singapore doesn't lack anything. So having lived here almost 16 years, my view is Singapore doesn't lack anything. Doesn't lack money, doesn't lack talent, doesn't lack infrastructure. What we need to do is believe that we can build globally relevant products and globally relevant companies. So that's it. That's what we're trying to do, and we'd like to work with anybody that believes the same. So now I think what we're going to do is hand over to Simon. We'll hand over to Simon to get us kicked off. Thanks again for joining us tonight.
Right, thank you, Steve. Sorry, I tend to throw my voice. I'm Simon, and I'm Simon C. The only relation I have with Steve is that our names start with the letter S. Right, and so I work for NVIDIA. So as you guys would know, NVIDIA is no more just a graphics company. We are actually an AI computing company. When Steve actually approached me just about a month ago about this SGInnovate, I was very excited because when NVIDIA started off doing all this artificial intelligence stuff deep learning, machine learning, and so forth. One of the challenges that we have in Singapore is to identify who are the people who are doing AI, who are the people who are doing machine learning. And when Steve told me that, well, he's going to build this fantastic place where we gather all the people together and so that people could actually collaborate, people to discuss and work together, I thought, wow, that's a great idea. That's fantastic. And I think within 5 minutes, we shake hands and say, well, we're going to go for it, right? So without much ado, I must say that we are very, very happy to be here with my team, Atticans, Terrence, Osana, and Sengmeng, and also some of the PhD students that is working with us in this AI is here too. Welcome again to this, and I'm really looking forward to actually meet up with many of you to see how can we actually work together. Thank you very much.
Thank you, Simon. Thanks, Steve. We have 5 very, very short presentations today. What we wanted to do is to have some teams come up here and share what they're working on, and then take your feedback or your questions. So first off, we have Dr. Attican from NVIDIA to share with us more of NVIDIA's work.
Sure. Hi, good evening, everybody. I'll make it short because it's the evening, not too heavy. Let me just quickly share with you deep learning. So from NVIDIA, we say this is a disruptive technology because we see changes are taking rapidly. It transforms many ways that people are doing things. It could be business process, it could be a task flow, it could be how we solve problems. So if you look at it, we have seen startups, about more than 3,000 startups worldwide in AI space, which is NVIDIA working with them. From cybersecurity, from genomics, from self-driving cars to drug discoveries, we see enormous changes, enormous disruptive technology coming from startups like y'all. And as you can see, a simple landscape which I borrowed from TechMerge. There's many companies and they go into domain specific. And I would definitely, we have been working closely with the startups in Singapore as well, from NVIDIA as part of the Inception program. I'm sure you fit into some of this particular domain. The very interesting part is, the next slide, as you can see, the journey how many of the acquisitions are taking place now. And NVIDIA are very happy to be one of the founding partner of creating the AI waves. We have been, NVIDIA spent more than $1 billion in terms of investment, coming out with a series of technology, whether hardware or software, being the world AI computing company to help startups like you all. Next, as you can see, we are only in 2016. There's a lot of opportunity to have, and we have seen from many of this marketing research, you have 500 billion opportunity for you to grab, whether as you sell your company or whether you roll out your services, as you can see. And what we have observed over a period of time, and the next slide I'll be sharing with you, AI is required in each and every industry. Regardless, you're working on oil and gas, you're working on smart apps in terms of logistics. If you are looking at in terms of fintech, if you look at in terms of media entertainment, all these area needs AI, and the number of companies are ever growing. So it is a very exciting time to be here, and NVIDIA is more than happy to be in the journey together with you. Next, if you can see the trend that we have gathered across, for example, from what we learned from Google, they have more data, they have bigger and complex AI models coming up, there is more computation is required. For example, in terms of Microsoft, when they released AlexNet, one of the algorithm, between 2012 to 2015, from AlexNet to ResNet, the complexity of the model has increased almost 16 times. That shows a lot of research going in, better discovery, better insight. And if you look at in terms of speech recognition from Baidu, they took almost 2 years of data sets to train. And today, the AI could recognize the Mandarin language superseding human capability, right? Which is a very small error rate. Next. And what we are seeing today is the AI computing model has transformed itself, where you have large data set, you train, you validate, and you deploy, and it goes to many type of devices. And we are seeing explosion of new devices with AI capability coming out, and NVIDIA worldwide working with those companies to develop together with them. And we are more than happy to be with your journey to develop such AI, new disruptive technologies and ideas to be rolled out, bring into the market. Next. And we have a whole range of the hardware, software ready, available for you to use. And if you look at it, the whole framework that we have, most of it is free. You can take it up and you can use it. And I'm sure you're already using some of them. For example, Cafe, Theona, TensorFlow, and so on. The next, as you can see, I want to share with you how we work. NVIDIA builds the AI reference hardware, reference software. We give it for the startups to the enterprises so that you in turn can take it up, develop your product. A very simple use case that we have done in autonomous vehicle. Can we just play the... So this is what we have done together, a long journey with Tesla. And Tesla is ahead of the competition 5 years. They use Drive PX from NVIDIA, a full autonomous vehicle, which will be announced in 2017. So we can see on the left-hand side all the cameras which comes in. It takes enormous data from the camera, LiDAR, and many other inputs to make a decision. And if you can see the dashboard, this dashboard is actually built by using NVIDIA GPU, which is just to display. And the back-end computing is done by Drive PX2 from NVIDIA as well. And I'm sure there's quite a lot of PhDs and masters working at it. There are a lot of complex scenarios where you need to look at. So for example, when the car drives and goes itself, there is an object, for example, the bicycle coming, and you need to have a confidence how much space that you have between the car and the bicycle. And in this case, you have landmarks that you need to look at, and the turning to be done in this particular junction. Where do you stop? The bicycle is crossing. It could make its own decision. And in this case, you're turning right. How do you stop? How do you move? So all these are decisions being done by the car by itself by having sufficient knowledge and intelligence. So one of the complexity in terms of AI for driving is driving in freeway and highway relatively simple and easy, but driving in neighborhoods much more complex because you have a lot of objects around. You need to be aware of school kids who are crossing and different type of complexity required. And they have a full confidence, Tesla has a full confidence that AI has solved the problem, and they will have so-called autonomous level 5 driving capabilities built in their cars in 2017. Some of the competitors announced they will have that in 2020 or 2022, but they are ahead with the competitors 5 years ahead. So that's what I call is a disruptive technology solving many of the problems that we have in the world. So NVIDIA would like to be part of your journey, your AI company, regardless it's health-based product, whether it is genomic, whether it is whichever area that you're looking at, we would like to help and work with you. And I take care of the Inception Partner Program in Southeast Asia. I think Oksana would have shared with you some of the cards. Join us. We have technologies to help you and assist you. Right? Yeah, I'll just, next.
Oh yeah, good. The universal sign for auto.
Yeah, this is the reference platform which we have shared with the startups. So same like what we are doing to get with you, we give you the reference platforms. So in this case, when we started with our AI car, it didn't know what to do when there is a cone. It just knocked, right? It didn't know where to stop. But then we trained over a period of time. It's about 3,000 hours of training, and it knows what to do next, right? Without lanes, it knows what to do if there is a car coming from opposite direction, right? In this case, the hands are off. There's a tree in front. What do you do next? Right? We just wave hands, it moves, right? So in this case, there is an object in front that what do you do? And if you see over here, it has to turn, right? It learns. So it's a hard problem. Over here, there is a cone, there's a construction. What do you do? So it learns in certain scenarios and it knows what to do next. Again, over here, there is a diversion. It has to know what to do when there is a diversion, right? So these are the knowledge which has been planted to the vehicle to make decisions. We train in one particular area and it has been deployed in another area where it knows how to adjust itself, right? And the marker disappears. How do you adapt? There is a lot of AI gets in. And in a difficult situation at night, there is no marks clearly saying there is your right side, right? It knows. And whatever comes next.
Got it.
The journey with you, right? Okay.
Oh,
No. No, the next one. I think we skip this. We have done this. Yeah. So in order to achieve this, what we have is, I'll run through quickly. Next. Over 3 years, we have seen 60 times of better performance of the platform which you can use to develop your algorithms and components. We've been working with SGInnovate. We'll make some of the technology available for you as well. And that will help you to build your AI solutions and enjoy the journey together with SGInnovate, and NVIDIA are more than happy to work with you. This is the GGX box. It has 170 teraflops compute capability in terms of deep learning, machine learning. The next, I think you have, next slide. So in terms of P4, P40, those who are, I saw some of the startups looking at image processing. P4 is very good in terms of deployment, and you have enormous capability in order to do int8 in terms of what we call is image per second. AI analytics, it's much better than FPGA implementation. P40 is a bit more, much more larger compute capability. If you look at it, available for you to take it up and use it to try. And we have TensorRT, another framework to accelerate your AI algorithms. This is also freely available. You can get it to use it. And this is for those who are looking at in terms of, it's what I call Drive PX2 for autonomous vehicle, being used by almost 250 companies worldwide now, and labs. This is the TX1 platform. Those who are looking at embedded systems, I think there's quite a number of companies over here using it. You have your own design, you have own solutions, good, explore, and NVIDIA will help you to reach out to the marketing, reach out to the potential partners. And so join us as part of the Inception Startup Program, and you'll have more benefits as you join together with us. Deep learning, expertise will be shared, hands-on training will be given. We are looking at some possibilities together with SGInnovate. We can run this training here. And GPU Ventures opportunity, and also you'll be signed up to the Emerging Companies Summit in US, where you'll be given access to the VCs that you can present to them and pitch to them, right? We have seen quite a number of companies successful in that particular space. And we would like to share that opportunity together with the SGInnovate in Singapore startups as well. Thank you very much. That's all from me.
Thanks, Atakan. Now we open up to the floor. Any questions for Atakan and the NVIDIA team on how they can help your AI startup?
Yeah. Maybe for me it was not very clear. Your offering, I understand the hardware part, but do you have something like a cloud-based service to be able to use all this hardware and infrastructure and everything? Is that how it works?
So today, all of the CSP, cloud service providers, carries GPUs. Alibaba, all of them have that AWS. So you can use GPUs, paid per service model, yes.
So you have your own separate from IBM?
NVIDIA don't have our cloud service, right? So all the cloud service providers, they have our GPUs and they provide service to you.
So we as entrepreneurs, what exactly are we getting straight away, right? I mean, of course you have got your own embedded system chips which we can use to make or design anything else.
Can we go to the previous slide? So in the previous slide I shared with you. So what happens is if you become our Inception program member, you'll have access to our solution architects who will advise you to build solutions. I think later we'll have some of the guys will be presenting. We've been working together with them. And these are what are the benefits that you get, right, as part of the Inception Startup program. You can go to the website, you can read a bit more. And actually we're working with Steve and the team over here, having some of these, for example, trainings to be conducted over here. And we are looking at possibility having the compute part as well to be made available for you through SGInnovate partnership. Sure. Welcome.
Great question. Any other question? Could I also ask for you to introduce very briefly your name and the team that you're working on before you ask the question so we can all get to know you better? Other questions for Atakan? Easy. All right, Atakan, thanks a lot.
Sure.
They will still be available to catch up one-on-one after this.
Yeah.
Next up, we have Shubham from Homask to share with us what Homask has been working on. Shubham? He's making his way from the pizza.
Can I leave my bag here?
Sure.
Hi everyone. I think before I start, the question that was asked just now was interesting because AWS actually has very old NVIDIA GPUs. So if you are looking for new GPUs, you can either approach the National Supercomputing Center. As long as you tell them that we are a legit startup and we want to do cool things, they are quite lenient. Okay, maybe this is not the right platform to say that. And you can also approach ACRC, A-Star Computing Resource Center. They are also quite lenient. If you want, I can help you make the introduction. So yeah, I'm representing Hallmark. Since I don't have a clicker, no. Go back. We'll figure it out. So we are a healthcare company and we believe that diabetes is a data problem. Actually, we want to solve chronic care, but we started with diabetes. Yeah, next slide. This is just some information on how severe diabetes is even in Singapore. A lot of people suffer from it, so it's a valid problem to solve. Next slide, please. Next slide. There is a lot of research which is ongoing on how to tackle diabetes using data. Next slide. So this is how we look at the spectrum. So there are the people who are pre-diabetic or pre-chronic conditions, and then there are people who have chronic conditions, again, early stage, late stage. And so of course the effectiveness of digital intervention programs decreases as you go from left to right. We are targeting the early stage diabetics with not more than 1 or 2 comorbidities, and people who are not diabetic yet, as in pre-diabetic. We are also working on institutional intervention where we help the institutions improve their capabilities to find out the patients who need urgent help, but I'll talk more about that later. Next slide. So again, this is sort of the same thing. There's healthy population at risk, then there's early stage, then there's late stage. We are trying to focus on at risk and early stage. Next slide. Next slide. So again, diabetes, of course, has medications and there's lifestyle. So before we took up this problem, we did a lot of research as to whether lifestyle programs are really effective. But apparently, yes, a lot of research suggests that if you just improve your lifestyle along with consistency in medicine, 58% times you actually improve your risk for complications. Next slide. So yeah, this is one of the products that Hallmark makes. It's a smart coach for type 2 diabetes. We give you, next slide. Yeah, we give you an app which enables you to, oh cool, this. Thank you, man, yeah. Okay, so yeah, of course you can take a photo of your food. You can send it to dietitians. The dietitians actually look at your food. Later on I'll show how we are trying to use image recognition to solve this problem. We have a connecting weighing scale, so whenever you step on the scale, it's a GSM scale. The readings get sent to our backend. We are trying to make our own activity tracker because data from other trackers, getting granular data from other trackers was proving to be difficult. You use glucometer. We have a paper published on this, but that's not so interesting. So yeah, these are the key elements of GlycoLeap. There's of course the Glyco Coach, where we try to nudge people into having better lifestyle. And later on, I'll share we have some goals like 0.5 to 1% reduction in glycated hemoglobin, or 5 to 7% weight loss. We have mobile apps and devices. So these apps and devices actually help us do some of the cool data things. They let us try to see which approach works for which person. And yeah, you get education lessons and so on. So it's sort of a holistic program, augmented by data. So this is what a typical dietitian on our platform sees. She sees a patient's progression. Again, whenever a patient logs the food, we try to automatically classify the food. The food classification works well for the same person, but it doesn't work so well generally because it's very hard to figure out how much sauce it has, how much was the serving size, and so on. So yeah, the focus here is on making the dietitian's job more efficient. So yeah, this is an entire 6-month program. You have so again, month 1 we send you the weighing scale, we send you a weight loss guide. Then month 2 we send you glycometer, local food guide, and so on. But along the way we track your food, weight, activity, and glucose. So again, these are the variety of ways we get the data. I don't think I need to spend more time on this. Again, like these are the different devices or apps. So yeah, these are the outcomes that we guarantee. At the end of 6 months, either 5 to 7% weight loss or 0.5 to 1% reduction in glycated hemoglobin. So yeah, this is, today I just wanted to take a plot of how our food ratings are going. So higher is better. So as you can see, as the weeks progress, people actually themselves start to eat better and better food. This is the average food rating per week over all our participants. Yeah, you can see what the rating means. So higher is better. So that means this is a good sign. I mean, these are just some anecdotal stories. I replaced the pictures and names. Yeah, you can see it's quite effective. Okay, so, but a problem that we stumbled on was how do we actually scale this up? For example, if we want to reach more users, we need to hire more dietitians. So we are not making a chatbot because chatting is quite troublesome on an app. But we are trying to, for example, if you see in this figure, the dietitian usually asks, hey, did you put any sugar in the coffee? Because the image cannot tell you that. So we are making a rule-based system. Again, these are the 2 non-interesting papers if you are interested. That sort of gave us the foundation. And then the chatbot can actually do this job for the dietitian. In this case, the chatbot can ask, instead of the dietitian, the chatbot can ask, hey, did you actually eat this whole serving, or did you eat only partially? Yeah, of course, and the chatbot, of course, uses the image recognition to augment the kind of rules. So the chatbot can enable us to reach out to more users without increasing a lot of time on the dietitian side. So as we were doing this, we were quite bored. So, okay, not bored, but yeah, we wanted to see whether we can actually do data science. So we participated in some competitions since last year, all the healthcare competitions that I could find on Kaggle and Cloud Analytics. And then once we were confident, we approached SingHealth. We said that, hey, we have this, we can do some sort of data science. What are the problems that you face? So as you can see, so we signed an RCA with SingHealth, National Heart Center. These are the problems. They wanted to determine long-term outcomes over 10 years on death, heart attack, and so on. They wanted to determine the cost of care. And because many times when complications happen, the cost of care increases and the patient is not informed in advance, and he's not on insurance, that creates problems. And we, of course, the hospital is interested in the cost of outpatient medications and so on. So actually using the data of a hospital is challenging because they make you go to a separate room with no internet, and like you are basically connected off from the world, which I'm not used to. So yeah, these are the things these are our AUC scores. Then we compared our AUC scores to various standards that are out there, and we are doing quite not that bad. Okay. Oh, sorry. So, but one thing that we realized was that just if we really want to make an impact in healthcare, just doing it on the patient side will not be enough. So we actually acquired a EMR provider in US it was a spin-off from Duke University. They have their EMRs located in these hospitals. So the good thing is that EMR actually collected data from mental health patients who do substance abuse, and so on. And so we have quite a big data set which we can use to do interesting things. On the right, you can see the different kinds of things that the database consists of. So yeah, by the numbers, it has data of over 500,000 patients, 9 million qualified clinical visits. So we are trying to build smart clinical decision support systems so that before the patient walks into a doctor's office, the doctor knows based on his previous visits what medications to give him, which will have the least side effects and so on. That work is also published. I'll show you later. And yeah, since David asked me that I can ask for help from the AI community, if any of you guys are interested in exploring or working with this data set, please do talk to me. It's a big data set, and actually I'm looking to see what are the things that can be done with it. So yeah, this is a simple, so again, this research was, in this research we wanted to see whether clinical decision support using our data are actually possible or not. So you see, you just enter the age, which the EMR already knows. You enter the age, sex, and race, and the condition of the patient, and it can tell you which are the disorders the person is likely to suffer from, which medications, etc. Yeah, that's all. Thank you.
Thanks, Shubham. And you guys might have noticed, this is probably the only AI event in Singapore where you will not be shown a few slides of what is AI, what is the difference between supervised and unsupervised learning, because 90% of the people here are technical, specially selected to attend this event. So any questions for Shubham?
So sorry, this is a plug, but yeah, if you, we are hiring and looking for very smart people to join us. So yeah, if you are interested, please contact us.
Questions for Shubham and how to use his data set? Anyone? Oh, we've got one question. Please introduce yourself and where you're from.
Hi, my name's Alex. I'm CEO of Tiger. We are an AI company. Was interested to know, what are your challenges with the conversation assistant that you tried doing? So just, for instance, we actually have one.
Actually, we are not trying to build a conversation assistant. What we want to do is to drive engagement. So for example, when the user comes into our app, we don't want the user to be clicking on insights, but we want to direct the user automatically. Hey, do you want to see, so let's say the person had 2 hypos yesterday. Hypos means like your blood glucose drops below normal. Then we want to actually alert the user about that. Second thing, when the dietitians are doing health coaching and they see the food pictures, oftentimes they have to ask things like, have you had, how much sugar does this contain? Is this skinny? Did you eat the whole thing or did you leave something behind, so that they can score the food better? So we are looking for our conversation bot to do that. It's not really a real-time chatbot, because we actually did try a real-time chatbot. The problem was that no one had the patience to write long messages. So it's more of like a prompter. Based on context, it gives you a few options. You select which one. Does that answer your question? No? Okay.
Any other questions for Shubham from Homask? All right. Thanks a lot, Shabam. Next up, we have Ashkan from Alum Health. He will show you guys a very, very cool device that he has made.
Hello, hello. I mercifully do not have a deck, so you do have to listen to me, possibly. I will try to be entertaining and interesting. When we started Alum Health, the first place we started doing healthcare is Afghanistan. Why did we try to do AI in Afghanistan? That's probably not front of mind for anyone here. Well, we looked at where people were having massive healthcare shortage, and it was all in developing countries. But there were guys in the US, Europe, Asia, everywhere that were actually using AI to try to provide diagnostic support, whether it's in radiology, whether it's in pathology, pretty much across the board. And when we looked at that, we said, well, none of this is ever going to reach Africa. None of this is ever going to reach Myanmar, Afghanistan, Iraq, any of the places that replacing a doctor with an AI-assisted doctor would actually be really meaningful. If you're doing it in Singapore, if you're doing it in the US, it's a nice to have. In Afghanistan, where the ratio of doctors to patients is hundreds of times worse than it is here in Singapore, it's a need to have. But we run into one really, really big problem in AI, which is everyone's sitting here saying, hey, send us all the data, or hey, National Health Center, give me all the data and we'll analyze it for you, and then we'll send it to you in a report on this is your results. Well, if you're in Africa and you're in Afghanistan or wherever you are, there's very little you can do without the data itself. And if it's sitting there siloed in a hospital in Afghanistan or a hospital in Nigeria, you're pretty screwed, actually. You can't run any of the algorithms you want unless you have a real good deployment strategy. So what I actually wanted to talk about today is, well, how do you go from we're sitting here putting algorithms up on SoftLayer or AWS or whatever it is, to we're actually deploying those at the point of care, at a facility, and actually reaching out to our patients or whatever AI execution methodology you're looking to have. It seems like us, maybe a few of the driving AI companies, and a few other companies are actually looking at how do we go from cloud-based AI to actually just in time, at the point of care AI. So what we did is we actually said, wait, if we can make algorithms up in AWS or anywhere else, if we can get a pretty big GPU, oh, that's nice, our website, thanks. If we can take a modern GPU and stuff it into a tiny little box like this, put on battery backup, run a bunch of fun kernel level stuff, what we're able to do is actually attach GPUs directly to CTs, MRI machines, mammography machines, and a whole slew of other medical modalities and provide higher quality healthcare today. So right now you see Google saying, hey, NHS, give us a bunch of data and in a few years we'll start giving you algorithms that will help you diagnose diabetic blindness. Well, today in Afghanistan we're already doing this. You guys probably haven't heard about it because you didn't stop by Afghanistan on the way here. But our boxes are actually deployed in a number of clinics in Afghanistan, in Nigeria, and we're rolling out throughout Africa and Southeast Asia. So why am I talking about this? Well, for us, the interesting thing is building in these deployment strategies and these data strategies into the beginning of a company. Because if you don't know how you're going to actually deploy any AI you're actually building, if you're just going to sit back and wait for the data to arrive to you, well, ultimately, there's going to be 15 different companies doing that same thing. Today, you can list off 10, 15 different companies that are sitting there and developing AI algorithms for radiology, for example, for pathology, for example. What we did was very different. We actually built a box and put it in a hospital. And so we actually were able to take the data at the point of care. And then on top of that, we built a number of fun little features that allow us to store and transmit data up to 10 times faster than traditional data transmission algorithms. Well, one, it was nice because healthcare is basically in the Stone Age. Because the way data is transmitted in healthcare is about 15 years behind how it's stored and transmitted anywhere else. So we said, wait, let's actually bring this to modern day, and we put that on our hardware and then gave that to the facilities. For the facilities, we gave them something that they needed today, which was higher quality access and higher data speeds than using traditional algorithms. And what that gave us in return was permission to access the data. But it wasn't permission in like a, here's your consent letter. It was, hey, we're providing you something that will make you want to continuously give us the data, right? And so I think that's what really differentiated us and allowed us to actually get traction at an early stage. It was going into geographies where there was real need and actually being able to bring something other than just the AI to the facilities. Because ultimately, AI is something that is a part of a larger value chain typically. Guys aren't looking for AI, they're looking for good diagnosis. You're looking to, if it's a self-driving car, you're looking to get from point A to point B. Whether it's AI or not is really not part of the question. And so, yeah, that's effectively what we've done. We've deployed our boxes in Nigeria, in Afghanistan. We're about to enter Ghana, Sudan, Indonesia, and a couple other markets we can't really talk about yet. And we've done this for tens of thousands of patients now, and we're going to be doing this for hundreds of thousands, if not millions of patients over the next year. And that's probably more than anyone's doing right now in medical AI, and we're doing it nice and in places where no one else is doing it. Okay? So I'll open it up to questions, if that's okay.
Questions? Please introduce yourself too.
Hello, can you hear me? Yeah, my name is Izhar Peri. Actually, my question is because you're doing the real life or real world and doing a transmission, do you guarantee the safety and security and privacy? Because this is healthcare and you need to take care of the security, which is different than taking the data from institutes.
Completely. So, there's a Hippocratic oath of sorts with medical AI, right? It's do no harm, but also don't show anyone the data. And so for us, everything is encrypted, secured at rest, secured on transmission. It's sitting on AWS behind their layers of security as well. And frankly, it's oftentimes far better than the hospitals. But what's really interesting is actually that a hospital in Afghanistan has the same problem that a hospital here has, except it's self-inflicted. In Singapore, hospitals don't want to send data up to the cloud. In Afghanistan, they can't send data up to the cloud. Now, just because your problem is coming from a different approach doesn't mean the solution isn't the same solution. So actually, when we took our hardware to San Francisco, we showed it to a number of hospitals in the US, and they said, wait, so you deploy this at a place like Afghanistan so that you can actually run your algorithms locally? And we said, yeah, because we needed to run them before we transmitted a gigabyte of data. And they said, wait, but this is actually really valuable if someone doesn't want to send the data out, period. So for us, it actually allows someone to access those algorithms without actually transmitting the data out, because the algorithms are what's coming in. And if they choose to allow us to store the images, which typically they do, then we also allow them a storage and transmission service so they can send their reports to India or the US or Singapore or wherever they want, so they can get just-in-time diagnosis. So I know that's a long-winded answer, but that's a really complex question too. Please, fire away. This is your time more than mine, I suppose. Anyone? Bueller?
Hi, I'm Shirish from Right Click. My question is, who are I come from India, so I can see a lot of utility. I wanted to know what size of hospitals, what size of clinics, who exactly can use it, and how does the pricing structure work?
Yeah, fair point. So we're partnered in India with guys like Apollo Hospitals. In the US, we have a doctor network, hundreds deep at this stage. And we deploy it in really large facilities in places like Nigeria and Afghanistan. Now, a hospital in Nigeria sees thousands of patients a day sometimes. I mean, I've seen doctors that individually see hundreds of patients a day. That's fascinating, actually. So for us, it's really across the map. It's people that either don't want to go spend hundreds of thousands of dollars on traditional radiology IT, or that want something that actually performs better than what they're used to. Because, as I was saying about the storage and transmission protocols, also the cost basis. That's using NVIDIA embedded GPUs. How much does that actually cost us to deploy? Sub $1,000. Now your traditional radiology server, I know GE sells theirs for low six figures, and for a hospital in Nigeria, for a hospital in Afghanistan, that's not something they're interested in paying. So what we do is we actually have it as a pay-as-you-go service. We give them the hardware and say, as much as you use it, we'll charge you. And the good part about it is we do this in bulk. And so we're able to actually push the price to a level that's affordable in those countries, as well as acceptable by our doctors in the US, India, and elsewhere. So, we've got tens of thousands of dollars just in Afghanistan where people have paid for external opinions. Why? Because those are actually big markets, right? Afghanistan spends hundreds of millions of dollars every year just on medical tourism, right? Medical tourism means I'm looking for healthcare outside of what's available locally. So that's effectively how we do it.
Hi, Malik. I have two questions.
Shoot.
Atikan from NVIDIA. So you are one of the Inception Startup Program member. Since we have quite a number of startups over here, maybe you want to share your journey as the Inception Startup Program, one. Second is, I know after 6 months, you're already in black, not red anymore. How was your journey as a startup from red to black within 6 months? And you almost going to reach 1 million people. And I think NVIDIA is very, very glad that you can transform people's life with your disruptive solution.
Well, at the risk of sounding like a bit of a commercial, the reason why we went with NVIDIA is they're actually kind of helpful when it comes to embedded development. I mean, we started with another company that rhymes with Balcom. And what we found was that, well, they didn't really have the GPUs that we needed, and the support was actually slightly less than we'd like. Obviously, this stays within this small room. And so when we moved to NVIDIA, we looked at it and said, we were originally on the K1 platform, and the performance was just per watt, just awesome when it came to deployment. And so for us, it was kind of an easy choice. And then once we started to get that going in our V1, it immediately made sense for us to then start designing for the X1. And literally the minute the X1 chips came out, we were one of the first people in line to get them. And we got an allotment through our contacts at NVIDIA. Even when the TX1 was coming out, we were getting nice little, I don't want to advertise this, but they were sending us free development kits, which are awesome when you're poor. So there was that end of it, but also, I mean, the direct line of contact with the tech team there has been fantastic. So basically, anytime we run into a problem, we just fire out some emails, and the engineers are helping us out to actually solve it. And embedded systems are not software wrapped in plastic. I don't know how many guys are doing hardware here, and neither me or my co-founder came from a hardware background, and it was let's say, a rather stiff learning curve, to say the least. Now I know far more than I'd ever like to admit. I can literally wire the entire box myself and put it together by hand, solder and everything. But that level of support. So basically, the minute we change to their chipset, we have really, really good support, and that's why we stay with them. And frankly, the X1 is just really by far the highest bang for the buck when it comes to the image processing per watt. So our boxes at rest are using something like 3 watts, and they can run right now. We do something like 18 hours on battery before it actually has to be charged in a given way. And in countries like Nigeria, where the power grid kind of sucks, being able to run relatively leanly and still be doing GPU processing is fantastic. So yeah, that's my plug for you guys. But yeah, no, and overall, realistically, the other nice thing about it, I don't know how much you guys have thought about how do you go from cloud to embedded systems, but if you can keep it all in CUDA, it makes your life really, really easy, because then basically your deployment looks exactly like what you had sitting on your servers anyway. And so for us, it made our cycle times very fast from the time in which we had a new algorithm to the time that we could actually put it on the box and deploy it. Because the way we do it is basically we have, petabytes and petabytes of data and medical images sitting on our servers here in Singapore, out at soft layer, I guess. And they're just churning through all the images. But then as we test and affirm a new algorithm for a new type of test, whether that's diabetic blindness, whether that's fallopian tube blockage, whatever it is, we do very specific tests. It's not like you look at an image and say, okay, this guy has X, Y, and Z. No, it's you test for a specific thing with each algorithm. And then so we're able to take it directly from our servers right down to the embedded systems, basically as easy as possible. That's something that's understated, how difficult that can be in terms of your cycle times. And that's why we stuck with CUDA. And on the NVIDIA embedded systems, everything can stay in CUDA. So.
All right. I think Alum Health is a fantastic example. I know there are a lot of AI startups here of how we can build from Singapore for the world and create very globally relevant products and companies from here. Ashkan, thanks a lot. If you want to know more about how to create a hardware startup, how to work in some of those countries, feel free to contact Ashkan. Next up, we will have a switch of frequency. We have Professor Xiao Wei, one of the leading minds in Singapore, to talk about his research at SUTD.
Oh, thank you. Hello. Okay, first of all, I want to embarrass a few people. So all the guys who are from SUTD, can you please, those who are sitting in front, stand up. Those who are standing, raise your hands. Okay, now look around. These are the SUTD folks. So after all the talks, please go talk to them. Okay, they have very interesting stories to share. All right. So my name is Xiao Wei. I am assistant professor at SUTD. We are working on AI research. Today, we kind of want to share a little bit of what we think the future of AI will look like. Okay, and at SUTD, we do a lot of applied work. We do a lot of we don't want to do theory for the sake of theory, all right? We are always pointing our theory at applications. So we are very glad to work with startups. And so if you see us around, feel free to come to us and say, hey, I have a problem. Tell us how we should solve this problem. We are very glad to work with you on that. And so what are we interested in? So in our group, there are two big problems we care about. The first is training massive neural networks. Okay, currently the biggest neural network in the world is about 200,000 neurons. We want to train 2 million, 20 million, 200 million neurons, which means we will need a completely different kind of training algorithm. So backpropagation is not going to cut it. So the second problem that we want to solve is machine reasoning. All right, and that's what I'm going to talk about today. How are we going to tackle the problem of machine reasoning? And so, all right, the standard stuff on deep learning, yada yada. And of course, in recent years, we've seen like how deep reinforcement learning has become very popular, and especially when this year, Google AlphaGo, they beat the world champion in Go using something called Monte Carlo tree search, okay, using a deep neural network. And so people are asking what's next? What are some of the biggest problems? And I think there's a consensus in the community that it's about common sense. It's about machine reasoning, and ultimately they want to write computers that can program themselves. Okay, so this is Skynet at work, right? Skynet. But no, not really, because I think people still feel we are really far from Skynet, but that's another conversation, all right? So the story really has to start with this guy. Anyone knows who this guy is? Yes, Yannis. Bertrand Russell, very good. Okay, Bertrand Russell, this is one of the fathers of mathematical logic. So we want to talk about machine reasoning, we have to go back to Bertrand Russell. And Russell is very, well, he at the beginning of the 19th century, he started quite a stir. All right, he started a stir with this thing called Russell's paradox. So at the time, people believed in mathematics, that they had already had the foundations of mathematics, but Of course, Russell said, hey, I can make a paradox by creating a set, R, that contains all sets which are not members of themselves. Is R a member of itself? All right, so this is Russell's paradox. And based on that, people tried to fix the hole that he found in the foundations of mathematics. There were two approaches. The first is called set theory, all right, or what commonly is called Zermelo-Fraenkel choice set theory, ZFC set theory. Very technical stuff. You don't have to know what that is, but at least you know that all the calculus you did in high school makes sense. All right? But Bertrand himself didn't really believe in set theory. He said, I think that the solution should be something called type theory. So he believed that every object has its place. They all have a certain identity. And you should not mix different things which are of different identities together. So you should not mix integers, for instance, with bananas, apples, and oranges. All right? And he believed that everything has a type. And you need to understand things from the point of view of a type. But that theory kind of got lost and pretty much went over to the side of the computer scientists. Today, we call it functional programming. In fact, type theory is the reason why we have computers today. All right, Turing machines, type, and then we have lambda calculus, programming languages, all came out of type theory. But mathematicians are starting to pick it up again, and they are coming to a theory called homotopy type theory. This is the latest that we have right now, 2009. And they were able to reduce all of mathematics to one axiom. And that's called the univalent axiom. So if you're interested, you can go check it out on the internet. So this is the guy who's very well known for homotopy type theory. You see the blackboard behind actually has the word homotopy on it. And univalent foundations, right? His name is Vladimir Vygotsky. Vygotsky, even before he came with homotopy type theory, he had already won a Fields Medal. And look at how young he is, all right? And so in 2009, Vygotsky proposed univalent foundations. And since then, it's really changed how mathematics is being done. Okay, and the effects are still being observed within the mathematical community. And I'm saying this because my PhD is in mathematics. I don't have a PhD in machine learning or computer science. My PhD is in mathematics. I can tell you that his work has made quite a big impact. And one of the important things in type theory, okay, is something called the Curry-Howard correspondence. All right, this is probably the most technical thing you're going to see from me today. So basically, in type theory, they say that okay, there's actually analogy between 4 different pairs of things. The first, all right, is the idea of a space and points in a space. The second is the idea of a type and different kinds of things of that type called terms. The third is the idea of a theorem and many ways of proving that theorem. So proofs are different kinds of things that prove a theorem. And the last, for computer scientists like us, we care about intents and implementation, which means that intent is actually what an algorithm does, and implementation is actually how you implement it, or how you solve that problem. And so I think the big breakthrough from 2009, okay, what we have really discovered in math is that in order to come up with a theory of mathematics for which it is very easy for computers to prove or check a proof, okay, or to automate a proof, is the idea of a type. Previously, when you did set theory, you never had to worry about types. You could always have a set that contains real numbers, integers, and bananas, all right? That wouldn't be a problem. But in type theory, that's disallowed. But by introducing types, we were able to get huge advances in mathematics. And so, if you carry forward this correspondence, it's basically telling us what we need to do in computer science is to study intents. Intent. You have to understand the intent of your function. You have to study intent of your algorithm. The machine needs to understand the difference between an intent and an implementation. Until you see this divide between these two terms, you're not going to get proper AI. Okay, so what is intent? So up there is a traditional program you'll write if you want to print a number from 1 to 10. All right, write a for next loop and then you do an output to the screen. But if you were to do intentional programming, you would start with the intent to print the numbers from 1 to 10, and then someone else could come along and break up the intent into smaller intents. Like, well, first I will need to have a function that prints elements of a list, and then I will feed to that function a list with numbers 1 to 10. All right, and then of course someone else is going to come along and decide what it means. How do you print a list, and how do you come up with a list with those numbers? All right, and so it's a very top-down approach to programming. And now you're wondering, has anyone actually done something like this? All right, the answer is yes. There's a software company called Intentional Software. It started out of Microsoft, okay? And pretty much since it left Microsoft in 2005, it has been in stealth mode. It hasn't really come out into public, but people who have been invited for their beta version workshop said that what they saw was mind-blowing. It was amazing, all right? But they couldn't share what actually they saw. But the idea of using intents is starting to creep into the AI community. Another company you guys may have heard of is Viv. All right, Viv.ai is also using intentional programming. It actually has an AI that takes something that a human asks, like whether it will be warmer, 70 degrees near Golden Gate Bridge after 5 p.m. the day after tomorrow, and breaks it up into smaller intents that the machine is able to deal with. Okay, so how is that different from what you already know in programming? So here's an example of a poor intent system or a poor type system. Currently, if you have a sorting function, in any programming language, the type of the function is that it takes in a list of natural numbers, okay, and it outputs a list of natural numbers. That's it. But to the machine, what does it see? It sees just a function from a list to a list. It doesn't understand what this function actually does. But a rich type system would be able to say that the sort function is a function that takes in any arbitrary list of natural numbers and spits out a list of natural numbers L prime such that L prime is a sorted list and L prime have the same elements. So this is a rich type. And so in order for machines to fully come to a place where they understand intents, we have to feed intents into a machine this way. But notice that here, the machine doesn't know how to implement the function yet. All it knows is this is what it's supposed to achieve, but it doesn't actually know how to implement that. But that's okay. So how do you do that? This is the secret sauce, the question mark that I'm going to only share at the end of this talk. All right, this is the hardest question here. But where do we go from here? Suppose we were able to do this. Where do we go from here? So what's going to happen in the ecosystem many years from now when we actually solve this question is that there are few critical services that's going to arise on the internet. The first service is that there will be many servers out there that will be able to convert intents into implementations. All right, you can actually take an intent, go to Amazon, go to some other company, maybe go to NVIDIA, and then their computers will actually take your intent and compile it into an implementation and run it. So you tell them, I want to sort, they'll actually do it for you. The second kind of service that will become important is the ability to check that the implementation matches the intent. This is a security problem. So by having intents or types in system, we are going to solve a big mass of security problems at the same time. And I know there are some blockchain folks in here, so I wanted to pull a plug here. That blockchain will become very important in this ecosystem. That once you write implementation, the implementation needs to be hashed. And then a blockchain will be able to check that the implementation was not tampered, okay, when you actually have the intent. So these are some of the critical services in AI that's going to arise out of this intentional intelligence framework. So, okay, now, lastly, I'm going to cover what is the secret sauce. Okay, how do you compile an intent into an implementation? Okay, so the key idea is that we want to convert those intents into some network or device primitives. And those primitives have to use the physical resources efficiently, which means that the way that you compile an intent on an Apple computer and versus an Android phone versus a supercomputer would come out differently depending on the resources available in a machine. So this really helps us. Okay, AIs will learn how to compile things based on the resources available. And the way that we do it is that it will look at previous intents that were compiled and try to use them to draw inspirations for compiling this new intent that they see, which means that the system will actually learn to compile more and more intents over time. Okay, so it's actually learning to program. This is an AI that's learning to program. It sees something is done before, and then it says, the next thing that I'm trying to do should be very similar. And lastly, okay, so this idea of drawing inspiration, they're called tactics. So if you go to homotopy type theory, the idea of using tactics to prove theorems is actually a well-known concept. And so eventually what you would have are systems that look like AlphaGo. They're going to do a Monte Carlo tree search among all the different tactics. And in order to find a way that can compile that intent, into an implementation. So to summarize, I know there's a lot of people in AI right now who care about recurrent neural networks and attention, ATTEND. But I think that we need to be looking at intent, not just attend, but also intent. Okay? Intent is what is going to help us to solve the problem of self-programming machines. Thank you.
Thank you, Xiaowei. Fascinating talk. Any questions about the future of AI? Questions?
Yes.
I find, my name is Sinue, I'm CEO and founder of Tiger. I find it incredibly refreshing to hear someone talking about AI from a symbolic approach rather than a mathematical approach in the neural network. My PhD is also in knowledge representation and reasoning. That's why I really appreciate and value your contribution. I'd like you to elaborate more. I'm sure you're familiar with semantic technology and how this helps to realize the ideas that you're presenting. I'd like you to elaborate a bit more on that, how you think those technologies and that, description logics and all these things can contribute to realize actually intelligent systems that are, in my eyes, come from the knowledge representation, not so much from the machine learning.
Oh, that's a very good question. So you obviously know your stuff. And I mean, because it's exactly what we're working on these days, okay? So we have a group of people, feel free to talk to some of our SUTD guys. But we've been looking at, for instance, Google recently came up with a neural machine translation, GNMT. Okay, so what's amazing about their idea is that they're able to come out with a neural representation of every language. It's not just a neural representation for English to French and another one for English to Chinese, but this representation is somewhat universal. You can use it to translate from any language to any language. So what we are seeing here is a split in knowledge representation of two kinds. First, you have a neural representation, which is extremely intuitive. On the other side, you have a symbolic one. And both are essential. You cannot get rid of the symbolic one because that's actually how you check if something's correct. And you cannot only have a symbolic one without the neural one because that's where all the intuition comes from. And so what we're doing is that we are going to feed mathematical theorems and computer programs to derive a neural intuition that could be translated into any machine language if we want. Okay.
Any other questions? One more.
Earlier you mentioned that you can use backpropagation for massive neural to calculate the gradient. So what do you use then?
We use something called minimum probability flow. You can go check that out. It's a 2001 paper by some folks from statistical physics. They're from the Berkeley Redwood Center for Neuroscience. So the idea is that by using a different objective function, so instead of using maximum likelihood, we use a different likelihood function. And using that likelihood function, the gradients turn out to be very nice and simple. And we have some experiments which show that they do end up doing what we want them to do.
Questions? All right, or else Professor Shao will take more questions afterwards. Thank you very much. Next up, we have Professor Georgios, also from SUTD. He's Xiaowei's partner in crime.
Awesome. Okay. So I know what you all be thinking, where are the mathematics? Well, this is the time, okay. Now, back. Yes. All right, so this is a Beamer talk, so there will be some math, but we'll try to keep it relatively more conceptual and not go into the hairy details, okay? But nevertheless, I would like to share with you some ideas I think are helpful and possibly give you a difference of point of view about objects that you're very familiar with. So I want to talk about two ideas, dynamical systems, game theory, and how are they connected with this research on artificial intelligence. Okay, so this is the two key ideas, and how do they come into play? All right, so a dynamical system is kind of a very fancy way of talking about systems that move, okay? So think, for example, like a space, 0, 1 squared, okay? and I'm trying to capture how a specific particle moves. Okay, and the time could either be natural numbers or like either discrete or continuous. It doesn't really matter. And I'm sure you all have seen some sort of like differential equation, okay, which is the simplest for sort of like version of such a system. All right. So what's the key tool? The key tool in the theory, let's say, of dynamical systems is, you know, I'm looking at a system and I get lucky. And I find a function that always, let's say, strictly decreases along the trajectories. And at that point I really celebrate because I know something very powerful, that every trajectory converges. Okay? That's powerful, but I want something more. Okay? So for example, like it could either converge to something like a local minimum or a local maximum or a saddle point. So ideally, I want to go towards something that's a local minimum. Is that the case? Well, actually, the story gets a bit complicated, especially if you go into large dimensions. Okay? Because what happens, as you see in these pictures, at these sort of like white points, the saddle points are typically many, many more than the local minima. Okay? So ideally, hopefully our intuition should hold that we actually somehow converge to local minima, but it's not clear what happens if you move beyond 3 dimensions. Okay? And okay, this is a cute mathematical problem. What does it have to do with AI? Actually, this is the problem of AI. Okay? AI is nothing more, specifically deep learning, it's nothing more than high-dimensional non-convex optimization. Okay? The function that you're trying to minimize is your prediction error. I want to minimize my error. And this function is on a huge dimensional space, like all the parameters of your like deep neural net. Okay? And here's the billion-dollar questions, literally the maybe trillion-dollar question. How can you design an algorithm that actually escapes these like bad saddle points? Okay? And a very concrete question is the following. Think of the algorithm that everybody's seen, the vanilla gradient descent. Okay? So I take a constant step size and I move in the direction like steepest descent. Does this always converge? Okay? This looks like a trivial question, okay? This looks like a question that should have been answered, and that the answer should be yes. But actually, this problem is pretty hard for 2 reasons. Well, first of all, remember now, we're talking about an algorithm. This is not a differential equation. And actually, algorithms define like non-smooth trajectories. So something that's like, you know, because I don't take an infinitesimal step, I take a big step, okay? So when you have a non-smooth trajectory, very many weird things can happen. Okay, so doing mathematics is very hard. The second thing is that like the actual topology of saddle points can be super complicated. Okay, I can create continuums that are like very, very hard, like to analyze. Okay. Well, the good news is that like in very recent work by the lab of Michael Jordan at UC Berkeley and work of myself and Panagias, we actually proved this very simple theorem, but very powerful. That says actually gradient descent works. Okay? It escapes and it doesn't need any noise whatsoever. You don't need stochastic gradient descent. Vanilla gradient descent works, and it works even if there's a continuum of saddle points. Okay? No matter how complicated the setting gets, it just works. Okay, there's 2 sort of like main ideas that come into play. Okay? So the first observation by the group of Michael Jordan et al. At UC Berkeley was that this algorithm, actually, if you look closely into the implementation, it's actually smooth in a very precise mathematical sense. Okay? So although it's an algorithm, the correct way to think about it is as if it's a differential equation. Okay? This is a very non-trivial observation. And actually, so this paper has just been published like this year. I think it already has roughly 30 citations. The reason is because it allows you to define new algorithms, which are sort of like use intuition from physics. Okay? The second observation, so the argument by Michael Jordan et al., it works if your fixed points are always isolated. Okay? But even in the paper, they posed an open question. What if the actual manifolds of equilibria can be very complicated? This is a very practical question because Such sort of like weird equilibrium sets arise from symmetries. And many practical problems have hidden symmetries. Like if you think images, they have like rotational symmetries. Okay? So with my postdoc Panagias, who's somewhere over there, we find like a really cute mathematical argument. Somehow, no matter how complicated these objects are, you can always cut them up in very small pieces. And so like argue about individual pieces and then stitch them back together. Okay? The details are as complicated as they sound, but the good thing is that the algorithm is very simple. Okay? And it just works. All right. First idea, like algorithms are actually systems. Okay? Here's the second idea. Okay, now we know that these algorithms converge to local minima. So now I'm getting greedy. Okay? I want to prove something much stronger. And I argue this is something you've never seen before. Okay? I want to prove that on average, my gradient does not just converge to a local minimum, but in expectation in some sense, I have performance similar to the optimum. Okay, for example, think of yourself as a hiker, and you move upwards on this slope. And I'm going to ask you, okay, what's the probability that you'll go to the higher slope? It seems that's more likely, right? So I would like to be able to quantify that. I would like to say that, like, okay, if I drop you randomly on your state space, and you start moving greedily, like gradient descent, then in expectation, with very high probability, I end up to a really good local optimum. Like, okay, so how on earth do you do that? Like, this is like, you need a totally new idea, okay? And this idea actually comes from something called like game theory, okay? Game theory is the mathematical study of interactions. It says like, there's me and there's Shawei, my partner in crime, and let's say we're thinking like, what sort of operation system, or let's say, what sort of like GPUs or we should buy. And there's like two options, There's NVIDIA, and then there's some really bad names. But the thing is, like, myself and Shawei, we have to agree, okay? So we have like two options. The lower option is an NVIDIA, so I'm the row player, and Shawei is the column player. And if we both agree, then we both buy the machine, okay? And if we both agree on the second option, we get a huge payoff, let's say. If we both agree on the other option, we get a bad payoff, okay? So an equilibrium, a Nash equilibrium, is a state where no one of the two of us can deviate and increase their payoff, okay? So I claim that there are three equilibria here. In the first equilibrium, we both choose the red strategy. In the second equilibrium, we both choose the second strategy. And there's a mixed one. The mixed one is each of us plays the first strategy with probability 2/3, and the second with probability 1/3. And if you look at this, then there's no way for me to deviate and increase my payoff. Okay? So there's three bad equilibria. And I want to claim that if you squint, then there is a clear analogy. Okay? The pure equilibria correspond to local optima of this common utility, whereas the mixed equilibrium corresponds to a saddle point. So actually, if I were to look at this sort of like system from above, I can encode all of the system on this plane, 0, 0, 1 squared, okay? So here, this point captures what's the probability that I play the first strategy, okay? The first axis is the first agent, and the second axis is the second agent. So for example, the point 1, 1 corresponds to the equilibrium where we both play the red strategy, okay, the first strategy. The point 0, 0 corresponds to the second equilibrium, and there is the 2/3 equilibrium in the center, okay? As we've proven, the set of points that converge to the mixed equilibrium is a zero measure set. It's the points along this line, okay? But here, there's something much more powerful seems to be happening, okay? The volume of the region of the attraction of the good equilibrium is actually bigger than the volume of the bad one. And if I were to actually make the good equilibrium better and better, its region of attraction gets increasingly better, okay? So actually with Yanis, we're able to quantify this and prove the following, okay? For some specific class of these sort of like common utility games, we can actually prove that their average expected performance under random initial conditions is indeed within a small constant of the true optimum, not any local optimum, the true optimum. And that's despite having like a huge gap between different local optima, okay? And we can actually do this in many dimensions. And what's the key idea? Here's like the key idea, okay? So what we were able to find in these systems, okay, remember, these are like gradient systems. These are systems where like the thing I care about, the error, becomes smaller and smaller and smaller, okay? We're able to find some orthogonal quantities that remain constant with time, okay? So if we go back here, now I actually have an algebraic description of this line. I say, okay, what is the function, what is the value of this invariant function at equilibrium? And I ask of you, what are all the points that agree with equilibrium for this function? By the invariance, all the points that converge to equilibrium must have the same value with the value of this function at equilibrium. So effectively, I can find a mathematical description for these objects and then compute volumes. All right. So plugging back into AI, actually, you can think of neural nets or actually any of these sort of like learning systems as a big game. What are the agents? The agents are the neurons. And they're all playing the same partnership game. Their common goal is to decrease the error. The common cost is the error. You want to get that to zero, okay? So as long as you can embed this theory into like neural nets, you can actually understand how to create algorithms that behave even better than local minima, okay? And this is exactly what you want to do it. And you can actually decentralize them, which is the other very powerful way, and run them fast, even in very large networks. All right, these are the two ideas for today. Thank you.
Thank you, Georgios. Any questions?
Beer time.
All right, they're going easy on you.
Yeah, thank you guys.
Right, so that marks the end of our formal talks and events. We'd like to encourage everyone to interact and just meet everyone else from other places you've never met before. Yeah, there's beer at the back, wine at the back. We deliberately got people from academia, from startup world to all mixed together for this reason. And please follow us on Twitter, Facebook, LinkedIn, hashtag SGInnovate, hashtag do innovate. And if you have any feedback on how we run things, who else we should get in, please email me, david.sung@sginnovate.com. Go to our website and let us know how we can contact you. All right, thanks guys.